This video is kind of a collection of topics that covers many basic properties of numbers and the basics of algebra, that kind of thing. To start us off, we're going to be talking about expressions. An expression in mathematics is a statement that doesn't have an equal sign. For instance, 2 times the quantity of x plus 3 cubed plus 1 and a squared plus a minus 15. Now, neither of these have equal signs, so they are expressions, and there's nothing we can really do with them unless the variable is given to us. So for instance, let's say x equals 7 and a equals 2. If the variable is given, then we can just plug them in and we can actually evaluate the expression. And we evaluate by using order of operations. So the first thing we do is parentheses. 7 plus 3 is 10. Then we do exponents. 10 cubed is 1,000. Multiplication and division is next. 2 times 1,000 is 2,000. And addition and subtraction is last. 2001. Same thing here. We do parentheses first. Now these parentheses don't actually mean anything because there's a single number on the inside. So we don't have to worry about that. Exponents is next. 2 squared is 4. Multiplication and division, there's none of that. And addition and subtraction is the last thing. We go left to right. 4 plus 2 is 6. And 6 minus 15 is negative 9. So when the variable is given, we can evaluate an expression to get a number. But that's about all we can do with expressions. On the other hand, if we have an equation, this is a statement that has an equal sign. And if a variable is given in that, we can solve for the variable if it's possible to do so. But also we can plug in the sample values to get values out. A formula is a type of equation that relates two quantities or more quantities. And here is a sample formula that it talks about tuition and during the year between the years of 2000 and 2015 approximately. So here we're talking about x is the number of years after 2000. In other words, x equals 0 means the year 2000. So if you wanted to figure out what does this model estimate for the year 2010, well, all we have to do is plug in x equal to 10 because 2000 is x equal to 0. 2010 would be x equal to 10. Plug the number into there, and now we just solve this thing using PEMDAS. 10 squared is 100. 10 plus 3310. And we can do multiplication and division. And doing the addition, we get, let's see, 6610, 7010. This is the estimate of tuition in the year 2010 for this model. Now we could, for instance, try and do 2020, which x would be equal 20 in that case. But this model was using the data from, I think, 2000 to approximately 2015, maybe like 2010, 2014. And if we were to try plugging in 2020, x equal to 20 in that case, this would actually fall outside the range of this formula, and that means it won't give a good estimate. So we're going to move on from this and talk about sets next. Sets are just a collection of things. They can be really anything. We're going to, of course, use numbers. A set is always given in one of three methods. The list method or roster method is where you're specifically given what's inside of the set. For instance, the set of 1, 2, 3, and 4. This is a list of elements within a set. And these curly braces on the sides here, this is how you know we're talking about sets versus other kinds of quantities. So this is the list method, where we actually list out the elements. We can also talk about a set using set builder notation. And that's something like this: the set of all x such that x is an even number. So that's a set builder, meaning you can use this thing to build a list. For instance, we could say that this thing is also equal to 2, 4, 6, 8, and so on and so forth. This, of course, is only the positive even numbers, so we'd have to also include the negatives. So we could say something like plus or minus 2, plus or minus 4, plus or minus 6, and 8. And of course, 0 is also included, so we have to add 0 into there as well. So those are the kind of things. A set builder is a nice way of using English to kind of make it simpler, but you're still using the mathematics. The last type of set is to just use English to say it. So it's called a declaration, like the set of all odd numbers. Each one of these things has kind of special uses. The list is nice to work with because you can visually see what it is. But sometimes you're working with infinite sets and they're harder to describe in a list, and they're actually easier to describe using the set builder notation, the middle one here. Of course, the English one is nice because it's probably the easiest to use to describe, but it's hardest to kind of translate into mathematics. We will typically be using the roster or the list method here on the top because we're not really working with any kind of special quantities. We're going to be just kind of stating what we're working with. Now, sets can have operations on them just like numbers. They're kind of like addition and subtraction. They're not really the same thing, but they're kind of similar to that. The first one is the union. The union is abbreviated with just like a big U. And this is saying, what is the most that I can have? So for instance, let's say I had two sets like this: 4, 7, 15, and 100. And I union this with the set of 1.3, 8.496, 7, and pi. What's the solution to this? Well, it's going to be another set, and we're just going to put every single element we can that's in one or the other. So 4, 7, 15, 100, 1.3, 8.496, and pi. And you'll notice I did not put the second 7 in here. That's because a set will only ever have one element of any kind at one time. There's no repetition allowed in sets. So this would be our answer to the union. It's every single unique element that is in either of the sets. The next type is called the intersection. And this is given the kind of N for intersection. And what we're trying to do here is we're asking what is common in both of the sets and what is the only thing that's common. So in the previous two things, so now instead of the union, we're going to do the intersection. This is asking what's in common, and the only thing in common here is the 7. So we say the set of 7 is the intersection. Like, where do they intersect? Where do they overlap? That kind of idea. Now, what if we had two sets that never overlapped, like this? 5, 6, 7 intersected with 10, 11, and 12. The answer here is a set with no elements. There is no intersection. And there's a shorthand note for this, and it's like this. It's called the empty set. It plays the same role that 0 does in the regular number system that we usually work with. So, for instance, like if we had a set of 4 and 5, and we unioned it with the empty set, there's nothing in the second thing, the empty set. So we only have 4 and 5 left. If we did the same thing, 4 and 5 intersected with the empty set, we would get the empty set. Now we're going to talk about sets of real numbers, the numbers that we normally work with, the real number line, and the breakdown of these numbers into special subsets. The first one is called the natural numbers, and these are also called the counting numbers. They're kind of the first thing you think about when you think about like the history of numbers. So you count 1, 2, 3, 4, 5, and so on, all the way on up to infinity. This is where kind of mathematics would have probably began, right? Just counting like how many animals you have, how many plants you have, that kind of thing. Now the next step is to look at the whole numbers. The whole numbers are actually the same thing as the natural numbers, except now we add 0. Probably one of the most important numbers in our number system. These are the whole numbers. And this symbol here in the very beginning, it's just, right, natural starts with an N, so you give it this double bar. The same thing with whole numbers, starts with a W. So you give it a double bar there to represent a subset of the real numbers. The next set is the integers, and this is given the Z. I think it's Z for some German word. And this is the set from negative infinity to positive infinity, and only the numbers that are that don't have a decimal part in them. They're just whole numbers, but you're also considering the negatives as well. Okay, the next set comes from the idea that we're working with parts of a whole number, and that is the rationals. Sorry for the cut there. I just needed to redo this section. The rational numbers are written as this, as two integers in a fraction. So A and B are elements of the integers. That's the Z things. That'd be, just to keep the continuity, Z is the things like -3, -2, -1, 0, 1, 2, 3, and so on and so forth. This includes all decimals that are ending. So for instance, 5.69237.591. This is a terminating decimal, so it is also a rational number. And infinitely repeating decimals. So like 13.456, 456, 456, and it can just continues 456 indefinitely. That's shown here by this bar. That is also a rational number. Of course, among everything else, like -3/2, that's a rational. -2/1, which is also equal to -2, that's a rational number. And these two numbers, 5.69237.591, we can rewrite this as 569237591 over, there's 1, 2, 3, 4, 5, 6, 7, 8 places. So we have 1, 2, 3, 4, 5, 6, 7, 8 zeros in the bottom. And that is an integer over an integer. This one can be rewritten And I'm not going to show you exactly how to do it. I recommend looking that up yourself. But I can rewrite it like this, which can be simplified to this. And of course, a mixed number can be changed into an improper fraction very easily. This is an integer over an integer. So rational numbers, they can be written as a list as the previous sets that we did before, but it's a lot harder to. And so it's easiest to use set builder notation to designate what are rational numbers. The irrational numbers is the next step, and that is given this I. And this one doesn't quite have a nice set notation. We really have to use just English to describe it. And it's the set is the set of all non-ending and non-repeating decimals. And you may think, well, how many are there, right? Pi, you know, there doesn't seem very many of those. Definitely rational seems a lot more. But it turns out the irrational numbers is way, way more than the rational numbers. It's called uncountably infinite, whereas the rational numbers are countably infinite. It's a much more advanced topic than this video is really covering. But there's some really interesting, mind-boggling proofs for it. And it's a very cool property of numbers that is in the everyday use of our number system. The last set we're going to be looking at here is the union of the rationals and the irrationals. So if we were to take the rationals union with the irrationals, this gives us the real number system. This is the real number line that you're used to using, the graphing system, Cartesian coordinate system that we use. Not 3, -2. These are all using real numbers, and they're the most they're the most complete system that's the easiest to work with. There is a more complete system that's called the complex system, which we will not really get into here because it uses the imaginary number I in it. That's just the set of A plus BI, where A and B are real numbers. They can be any one of these previous sets that we've discussed. That's like the most complete set that we have, but the real numbers are more approachable, and so that's what we kind of stick with and work with, is the real numbers here. And that's how the real numbers are formed, by unioning the irrationals and the rationals. So these things are all connected, especially because they're all real numbers. Let's just take a look, kind of like a Venn diagram, to show how these things are broken down visually. So if I were to take a box here and say this box contains all of the real numbers, then technically there'd be a whole lot more irrationals. It'd be kind of more like a line like this, and all of this would be the irrationals. That's hard to look at, and so I'm going to split it more like half and half. But just know there are way more of these than anything else. The rational numbers. We know there's this divide here, right? Irrational is every non-ending, non-repeating decimals, and the rational is ending or repeating decimals. So we know there's a divide there. Now, how does the integers play in? Well, the integers here, this z, right? If we consider b equal to 1 here, then a can be anything, and we get all of these integers, right? A can be -1. If a equals -1, then a over b equals -1 over 1, which is -1. And so -1 is within the rational numbers. In fact, all of the integers, all of these things are contained within the rational number system. So we can kind of create this little box inside of the rational numbers and say, this is where all of the integers reside. Now, likewise, if we go up here to the whole numbers, well, you can see the whole numbers right here, right? 0, 1, 2, 3, 4. That's just right here. 0, 1, 2, 3, 4, up, all the way on up. So the whole numbers are definitely within the integers. And of course, do it like this. These are just right there. So the natural numbers are contained within the whole numbers. So we can just go like this and do natural numbers. So natural numbers are within the whole numbers are within the integers are within the rational numbers. There's a divide between rational and irrational, but if we combine them together, we get the real number system, which is this entirety of the box. And that's what we're going to be working with for most of this class. Now, if I were to ask you, what is 4.67? What are all the classifications you can give for this number using these sets, real number sets? Well, first off, we know it's a real number, so we can give it the label real. What else can we give it? Well, it is a terminating decimal number, which means we know it is rational. Is it anything more? Integers, right? Integer numbers here are these numbers that don't have decimals. And this one does. So we know it's not an integer. And therefore, if it's not an integer, it's not going to be a whole or a natural number. So 4.67 is only a real and a rational number. What about 3? Well, 3 is definitely a real number. I could think of this as 3 over 1, which that would be a rational number. It's definitely an integer, right? You can see it right there, right here. So it's an integer. It is in fact also a whole number and also a natural number. So we can call it whole number and a natural number. So that's all kind of the classifications for 3. How about E? Well, I told you this one before. E is real number and it is irrational. And as you can see, there's nothing else in this box here. So that's the most it can be if it's irrational. It's going to be both real and irrational. Let's do square root of 2. If you type this into your calculator, it would, of course, round it off. But this number, and you can see proofs for this, very simple proofs, but a little bit more kind of abstract. And it's quite clever, very, very brief kind of proof. But it is a real and it is irrational. And so there's kind of breakdowns of some of these numbers and labels that we can give them. Okay, let's move on to the real number line here. The real number line is just a graphical representation of the real numbers we've just been discussing, right? Here I'm graphing all of the integers. But within the integers, in between here, right, these portions here, these are all rational numbers or irrational numbers, whatever you might have. And because we can graph them all out quite easily on this line, this is why it's called the real number line. We can always graph 2 numbers on this thing, and we can see which one is greatest and which one is least, right? -2 and -3. I can graph -2 by putting a dot there. I'm going to do it in red. And I can graph 3 there. And it's quite easy to see which one is greater and which one's smaller, right? The more right they are, this is going towards the positive infinity direction. This is going to negative infinity. This direction is the greater. So 3 is greater than -2. It's a higher number. It's like a bigger number. Think of it like that. What about distance for this? We can see 3 is greater than -2. And then we can also ask, what's the distance between 3 and -2? Well, we can look and we can say, well, 3 is 1, 2, 3, 4, 5 units away from -2. So the distance should be 5. How do we do this mathematically? Oh, quite simply, we use the difference operator. We use subtraction. That's how we find the distance along the real number line. So 3 minus -2, that becomes 3 plus 2, which we get 5. And that is the distance between these two things. But distance should be the same thing either way, right? Like if we were to look at the distance between -2 and 3, we should still get 5 units because they are in fact 5 units away from each other. But if we did -2 minus 3, now we get -5. And so that's not the same number as 5, right? So we need to redefine how we evaluate a distance. And we do this by defining absolute value. Now, absolute value has rich definitions in the fields of mathematics called topology. It's got a lot of useful things here, but in this simplistic of a view of it here, pretty much absolute value just takes the positive of numbers on the inside. As long as it's just numbers, that's really all it's going to do in the very end. You have to, of course, simplify everything first before you can take the positive result. But the absolute value of 3 minus -2 is going to always equal the absolute value of just the two things flipped around. And that's how distance is formally defined. It's going to be the absolute value of a minus b, and it doesn't matter which position you put it in. So the absolute value of 3 minus -2 is going to be 3 plus 2, which is the absolute value of 5. And the absolute value just says take the positive of whatever's on the inside. So 5 is positive, and then so you just leave it as positive. On the other side here, we get the absolute value of -2 minus 3, the absolute value of -5. And since 5 is negative, we're going to take the opposite of it. In other words, take the positive result, and we get 5. And you see we get the same thing both ways. So the absolute value will always give you a positive result, unless, of course, we're looking at something like, what's the distance between 3 minus 3? That will give us the absolute value of 0, which is 0, which is neither positive nor negative. But as long as the absolute value is the only thing there on the outside, then it will always end up being a positive answer when you have just numbers within the absolute value. Got a couple problems here where we're just going to simplify the expression, and we're going to use order of operations to do so. First step in order of operations is PEMDAS. First step is parentheses. And we always treat a fraction bar as having parentheses around the top and the bottom. But any kind of function, especially the absolute value function, that can also be thought of as parentheses. So I'm going to deal with the inside of the absolute value first, and then take care of the top and bottom. So inside the parentheses, we still do order of operations again. The next step would be exponents. 1 squared is 1, and 2 squared is 4. 1 plus 4, or 7 plus 3 minus 7 squared. 1 plus 4 is 5, and the absolute value, so this is just 5 here, the absolute value of 5 is, well, it's just positive 5. And you see that the 3 is multiplying the absolute value of 5. Okay, now we can take care of stuff on the outside. So we can take care of exponents first. 7 squared is 49. So I'm just going to rewrite this this 7 squared here. I'm just going to rewrite that as 49. Okay. And we can do multiplication and division. We have to work left or right. So on top here we have multiplication and division. I'm going to work that way. 52 divided by 2 is 26 times 3 times 5 over 7 plus 3 minus 49. 26 times 3, use a calculator for that, gives me 78. And then 78, so this is 78 here. 78 times 5 gives me 390. Now on bottom, I can do addition and subtraction because all the multiplication and division are done, except for the fraction bar, right? But that's always going to be last because you treat the top and the bottom as having parentheses. So we need to get done with those two things first, and then we can do the fraction bar. Okay, we can work left to right here. 7 plus 3 is 10, and 10 minus 49 is negative 39. And now you see we can do the fraction bar here. Positive divided by a negative is negative, and 390 divided by 39 is 10. So we've simplified this down and we get negative 10. Okay. This one here has, I'm going to add in a y here just to make it a little more interesting. And this one here has variables in it. So we have to always consider, are there like terms? But to simplify this, we still need to do order of operations. I'm going to start with the innermost parentheses. This group here doesn't have anything I can do. They're not like terms, so I cannot combine them. So I'm going to go on the outside parentheses, so this green thing here. And the first thing I'm going to do here is distribute the negative to get rid of the parentheses. It gives me 8y minus 7, 5 times negative, or 5 minus 7y. Negative times 7y is negative 7y. And negative times negative is a positive 2. Now the brackets, if you don't know, the brackets here are just another form of parentheses. It's to make it a little bit easier to see. Well, we have brackets here, so those go together, and we have parentheses here, so those go together. That's the only reason why we use different sets of separating type things like parentheses. Okay, I have like terms here. I have 5 and positive 2. 5 plus 2 is 7. Bunch of 7s there. And now this here has no like terms, so we can move on to the outside. I'm going to distribute the negative 7. Negative 7 times 7 is negative 49. And negative 7 times negative 7y is positive 49y. And now you see I have like terms. I can combine them to give me 57. Is that right? Yep. 57y minus 49. You can also write this as negative 49 plus 57y. Either way, you get the correct answer. And that's how you simplify expressions with and without variables.